Thank you very much to the organizers for what promises to be a very interesting conference. As long as I can find the chalk. Okay, so today I would like to talk about joint work with my student Songhao Lee. At University of Toronto, and this is part of a kind of larger project which our group is working on, which has to do with basically bringing in tools from projective algebraic geometry into Poisson geometry. And my other student, Brent Pym, who is also here at the conference, has some work in this direction, and both of them will be presenting posters. So I encourage you all to first of all go to the poster session, and especially if you want more information about what I'm talking about, to look at their posters. Okay, so a log symplectic manifold is something I learned about at Poisson 2004 from Olga Radko, who studied the two-dimensional case and discovered some pretty amazing things about these manifolds. So a log symplectic manifold is a Poisson manifold let's say the dimension is 2n, and it has a very simple condition placed on it, which is that the Pfaffian, which is the top power of the Poisson tensor, vanishes transversely. Okay? So, if this is the determinant line bundle, then the Pfaffian basically is going to be vanishing transversally, which means that in some regions you're going to have, let's say, a positive symplectic form, and in other regions you'll have a negative kind of symplectic form. I say positive and negative if there's an orientation placed on the manifold. Of course, the manifold need not be orientable, and so in that case, I don't really have anything to say in terms of positive or negative. The important thing is that the way it crosses zero is in a transverse way, and so right away you see that the degeneration locus is a closed hypersurface. So it's an embedded hypersurface in the manifold. Okay. And so let me give you some examples. First of all, the model example, the example that you should always have in mind. On R2, okay, this is a log symplectic form. Okay, this is the x and y axes. So here it's symplectic. It's symplectic away from the y-axis, and it's exactly zero on the y-axis. So in this case, the degeneration locus is indeed an embedded, closed hypersurface in the manifold. This is x equals 0, yeah? Okay, so the second example, let me just draw it. Let's suppose you had a Riemann surface, or a two-dimensional manifold. Okay, you could have a two-dimensional manifold. So in that case, the degeneration locus should be an embedded hypersurface, which is therefore a collection of circles in this case. So you'll have a circle here, suppose, another circle there, and there could be some collection of circles which are not zero, which are zero in homology, so say. So this is a torus with 3 degenerations. You could imagine that the symplectic form is positive here inside, negative here, and positive here, and it crosses 0 in these 3 locations. Okay. Another example, just to show you a non-orientable one. So if you take RP2, right? Then if I take a Poisson tensor, which is g of x minus y squared dx wedge dy, okay, where g of x is x minus 1, x minus lambda, okay, a cubic polynomial with 3 zeros. So this I've written this in R2, but if you work out the other coordinate chart, it does extend to the line at infinity, and you end up with a degeneration locus which is exactly this cubic curve, and that looks usually like this, in the way that people normally draw a cubic curve. Okay, and then you see here that although this component of the degeneration locus, this component, they're both components of the degeneration locus are circles. This one has an orientable normal bundle, and this one has a non-orientable normal bundle. Okay, but nevertheless, this is a log symplectic form. And then another example, which I'm not really going to talk very much about, is that if you take a generalized complex 4 manifold, okay, of the type that occurs in my work with Giù Cavalcanti or in the paper of Rafael Torres, these things look like a 4-dimensional manifold which is generically symplectic and which changes type along a collection of T2s which are complex. And if you do a real blow-up, on the T2s, you end up with, actually these T2s in those examples, they have trivial normal bundle, rank 2 normal bundle, and so the blow-up will be just T3. You'll have a T3 exceptional divisor, and that T3 will be the degeneration locus of the log symplectic form. This is only for people who are familiar with GC4 manifolds. If not, it doesn't matter. There's plenty of other interesting examples. Okay, so why is it called log? Okay, so this is a subject that, so as I said, there's a few people who have worked on these Poisson manifolds. One of the papers is from about 11 years ago, 12 years ago, by Ryushi Goto, where he called them log symplectic manifolds, which is why I've used that name. There's also the work of Radko, who called them topologically stable Poisson surfaces. She was only interested in the dimension 2 case. And then recently there have been 2 very interesting papers by Gilliman, Miranda, and Pires, who call them B symplectic manifolds, as an homage, let's say, to the methods of Melrose in the so-called B calculus, which they use in their paper quite a lot. But these are all the same thing. They're just transversely vanishing Pfaffian Poisson manifolds. Okay, but let me just explain why it's good to call them log. So consider this. So let's look at this hypersurface D, and then I'm going to define a Lie algebroid. These are the vector fields which are tangent to D. Okay, so this is a Lie algebroid. And so anytime you have a Lie algebroid, you have an associated Daram complex. So its Daram complex is, of course, the exterior algebra on the dual, and this is well known from the work of Deling. It's called the logarithmic Daram complex because of the fact that it's generated by, instead of just dx, dy, dz, okay, the way that the usual Daram complex is generated, this one is generated by dx over x, where d is exactly the zero locus of x. And of course, this is just d log x. So for this reason, Deling called this the logarithmic Daram complex. And so the kind of the first thing that you might want to check is that pi, so pi is a bivector field on my log symplectic manifold. Suppose I invert it, this defines not a smooth two-form. It can't be smooth, of course, because pi vanishes along D, or at least the top power vanishes. It drops rank along D. Okay, but it is a two-form in the log sense, in the sense that it has this dx over x. I mean, you can see right here, if I invert this, I get exactly dx over x, wedge dy, and so obviously it's in the log complex. But anyway, the important thing is that this thing is closed and non-degenerate in the sense of this Lie algebroid, and so it makes sense to call it a log symplectic structure. And there are a lot of people who have started, I've noticed a few papers recently about symplectic forms on general Lie algebroids, so this would be the simplest case after an actual symplectic form. Okay, so the thing that I need you to know about these things is the structure of the degeneration locus. So these are two-dimensional, so the structure is very simple. The symplectic leaves are just a bunch of points, right? The symplectic leaves for this degeneracy locus are just a bunch of points. But in general, it could be more complicated. So the degeneracy locus so the way that it looks, let's see, without going into too much detail. So pi to the n, it vanishes transversally, right? So this means that along its zero set, I can take its derivative. Okay, and this will be a conormal tensor so it'll be a co-volume tensor conormal because I'm taking derivative, right? And then actually what you can show is that this is actually a non-vanishing section of the determinant of TD. In other words, in wedge 2n minus 1 of TD. So here you could think that there's a trace, there's a contraction. You could take this conormal and hook it into here, and you get exactly an isomorphism to the top power of the determinant bundle TD. So this is non-vanishing. Okay, so in other words, this degeneracy locus, it automatically has a co-volume, which you could invert because it's non-zero, and you could integrate it, and so it has an actual volume. If the thing is compact, then there's a number associated to it, which Radko called the modular period. So this is an example of, this is a version of the modular period, and indeed, this is it's an example of a modular residue. Okay, which you can get from. Let me see. Instead of going into great detail, I'll just say this: that just for those people who are familiar with this, so the canonical bundle of the manifold M, right? We know that if we have a Poisson manifold, the canonical bundle is always a Poisson module, right? So the anti-canonical bundle of M is still a Poisson module. If we restrict it to D, this coincides with the normal bundle of D, and this is still a Poisson module. Okay. This is also just a real line bundle, so I can choose a flat connection. So if I choose a flat connection, out pops a Poisson vector field. Okay, so this is a standard construction whenever you have a Poisson module. If you're able to choose a flat connection on it, then you can write the Poisson module operator as pi composed with the connection plus a Poisson vector field. Okay, and then if I take this Poisson vector field, which is not canonically defined because it depends on the choice of the connection, right? If I wedge it with the top power of the Poisson tensor, okay, then this gives me exactly this d pi n. Okay, so this immediately gives us the following picture. So this is a picture of D. Okay, so D, let me put the D here. D is foliated by symplectic leaves. Okay. It has dimension 2n minus 2, right? So, okay, D, remember, so M has dimension 2n, right? This is a picture of M. Okay. Inside M, you have a hypersurface, D. D has dimension 2n minus 1. But D is a Poisson hypersurface, so it is a union of symplectic leaves. And the dimension of those is exactly 2n minus 2. How do I know that the Poisson tensor has maximal rank? Well, that's because, by assumption, this thing was non-zero, and it's equal to this. And here you see the top power of pi on D. So that tells us right away that that pi has maximal rank on D. Okay, but so if we take one of these symplectic leaves, okay, then notice that I have a Poisson vector field which is transverse to that leaf, right? Which means that there is a Poisson vector field transverse to this, right? Which tells me that I can move to the next Poisson, the next symplectic leaf, right? And so, just to make my life simple, we'll say that the m pi is proper. Okay, when it has compact leaves. Okay, so if it has a compact leaf F, then the existence of this vector field means we can drag this over and foliate all of D by leaves that are symplectomorphic to F. So inside Gilliman, Miranda, and Perez's paper, you'll find a proof of the fact that D, under this assumption, D is actually the mapping torus with respect to some symplectomorphism of F. So in other words, this thing here, this whole thing, fibers over the circle. Okay. For every point on the circle, I have one of these symplectic leaves F, which is a compact symplectic manifold, and this completely describes the structure of these log symplectic manifolds. So as you can see, the geometry is very simple. It's almost everywhere symplectic, except for a hypersurface, which itself is foliated by codimension 1 symplectic leaves. That's all you have.
Is this D a modular vector field for D?
Yeah, essentially, yes. It's a vector field that comes from a Poisson module structure on the canonical line bundle of M. So it comes from the modular class of M. Okay, and another thing that they proved, okay, is that there exists a neighborhood of D which is ichthyomorphic to the linear Poisson structure on the normal bundle. Why does the normal bundle have a linear Poisson structure? One way of seeing it is that the normal bundle is a Poisson module of rank 1, and on such Poisson modules there is always, on the total space, a Poisson structure. So, but this is a Moser type result which they proved for these things. So this really does describe every part of such a manifold. Okay, so the question that I had when I learned about this, I didn't know anything about symplectic groupoids, but I was impressed with these types of Poisson manifolds. And then later on, maybe at a different Poisson conference, I learned about symplectic groupoids, and so it became obvious in my mind to ask the question: what are the symplectic groupoids of these things? Okay. Can we classify them? Can we construct them explicitly? Right. I mean, the existence of the symplectic groupoids thanks to the work of CF squared, we know about the existence of symplectic groupoids in this case. So they do exist, but that doesn't tell me what they are in some geometric sense. I would like to actually study their symplectic geometry, right? This was the motivation behind this question. It's not enough for me to know that they exist. I would like to know which symplectic manifolds they are, how to construct them, how to chop them up into pieces, etc. So let me just make this a little bit more precise. So, of course, the cotangent bundle, okay, so the cotangent bundle is a Lie algebroid, as it is for any Poisson manifold, and I want to classify. So this is a kind of category, or maybe if you prefer, a lattice of possible integrations. And I want to know what this is. I would like to know the structure of this. Oh, and also, I would like to know which ones are Hausdorff. Okay, this is another slightly, well, for some intriguing, for some annoying fact about the symplectic groupoids is that because of various important examples, we tend to allow the total space of the groupoid to be non-Hausdorff, possibly smooth but non-Hausdorff. But I would like to know which ones are Hausdorff, and I kind of want to eliminate the ones that are not Hausdorff, but I'm told that that's not a good idea. But anyway, so which ones are Hausdorff? And actually, by the way, what about the same question for this Lie algebroid, which is not the same as this one, right? This is, remember, the vector fields which are tangent to D. These ones are kind of the vector fields which are not only tangent to D, but also tangent to the symplectic leaves F. Right, so this is a Lie algebroid that is natural from the Poisson point of view. But if we forget about the Poisson structure and only remember the hypersurface, this is the Lie algebroid that you have. And so I would like to know, what about this one also? What are all of its integrations, and how do you classify them, and which ones are Hausdorff? Okay, so this is the purpose of our paper. That is what we accomplish in this paper, to solve these questions. And I would like to kind of give you a flavor, a little bit of information about how we do it. Now, the way that we wrote the paper, we tried to write the paper in such a way that the methods could be kind of contained in little chunks, that hopefully you could take this chunk and use it for other classification problems. So I'm hoping that although it's a slightly long paper, you don't have to read the whole thing. You could just take a piece and use it. They're kind of independent pieces. Okay, so I would just want to talk about two methods for construction. Okay, the first method is a birational construction. It's a blow-up construction. Okay, and this one is inspired by work of Weinstein, Matteo Melrose, and Claire de Borg. Okay, these are the main sources for inspiration for this construction. The second is a gluing construction. When I say gluing, I really mean that you have a groupoid over, and then I have another groupoid, and they have an overlap, and I just glue them together, and I get another groupoid. Right? This is something which is kind of rare in the sense that groupoids are global objects. Right? You can't really glue them together in this way all the time. It's rare that you're able to do this, but we explain when you can, at least in some cases. So, and this is inspired by a paper of Nister. And these were papers that appeared around the time of CF squared. But they were thinking of groupoids. They were thinking of constructing groupoids in a very different way from the way that those four authors did. Okay, so let me say something about blowing up. This is something that when you go through customs you're not supposed to talk about. The title of your talk, if you. Okay, so blow-ups. Okay, so what is a blow-up? You have a submanifold. Hopefully it's a codimension greater than 2, otherwise the blow-up doesn't do anything. So if we have such a submanifold, we replace, so the blow-up of M along L replaces L with all of the different directions, all of the different lines which are normal to L. So it replaces it with the projectivization of the normal bundle of L. Okay, so let me just draw the canonical picture of a blow-up. So this is M, this is L. As you can see, L is a point, so it's codimension 2 inside M. And if we blow it up, what that means is that we must remove L, so now we would be left with a punctured plane. And then we have to replace it with the set of lines through L, and that set of lines is the projective RP1, and RP1 is a circle. So you end up with a picture like this, that I've replaced it with a circle. So you could think of it as having a boundary, but then I identify the boundary to make an RP1, and then I get a closed manifold. It's not a manifold with boundary. Okay, so this is just an RP1. Yeah.
If you say it's a set of lines, are you identifying the opposite points, or you keep them there?
I identify the opposite points. In the work of Melrose, he's very careful to do an oriented blow-up where you don't identify, and in that case you get a manifold with boundary. And that can be interesting to consider groupoids with boundary, but I'm not doing that. So this is an RP1 which is embedded in here, and so that means that when I do this, the exceptional divisor, this is called the exceptional divisor. Okay, when you do this identification, then its normal bundle becomes non-trivial. It becomes the Mobius band around there. Okay, so that's what a blow-up is. Okay, and the important workhorse, the kind of the way that you can work with blow-up in the easiest way is to know something about its universal property. This is not exactly the universal property, but it's a kind of geometric version of it. So there's a property. Okay. If you have, let's say you have a map of something into M. Okay, and of course you have this L sitting inside M, and then you have the blow-up. The blow-up comes with the blow-down map, so-called blow-down, down to M. And so there's a question, if you have a map from X into M, when can you lift this, right? When can you lift this? And there's a nice criterion, which is that if F has a clean intersection with L, then there's a unique lift. Okay. Alan mentioned clean intersection in his first talk, and clean intersection is a nice condition which you should learn about, but it's usually not phrased in terms of a map. So let me give you two special cases. Okay. So if this map is actually an inclusion of a submanifold, Okay, then what this means is that I need clean intersection with L. Okay, so for example, let me show you something that has clean intersection with L. So if I just have a line, right, or maybe a path like this, right, then what's going to happen is that it'll become something like this, like that. Okay? So this is an example of something that has clean intersection with L. Now, it's not transverse, of course. I mean, if I deformed it, then it would totally miss L. So this is definitely not a transverse intersection. It's clean intersection. And this is called the proper transform of S. So this is S. Okay? So if you have a submanifold with clean intersection with L, then you can lift it. And then something a little bit better is that if we take this map F and we check that the pre-image of L is a hypersurface, okay, if it's a hypersurface inside X, okay, then you could think about how F behaves normal to that hypersurface. So it would take the normal bundle to this hypersurface to the normal bundle of L. And if the normal map of F from the normal bundle of this, let me call it Y, if this hypersurface, if this is injective, then the map lifts. Then it satisfies this cleanliness condition. Okay? So it's just a very convenient kind of property so that we know whether certain maps lift to the blow-up. Yeah? Okay, 1 second. Say it again?
F is equal to L, and F is the inclusion.
If F is equal to L, yeah, then what happens is that the lift, the proper transform would be just the whole exceptional divisor, I think. Yeah.
Then the lift is not.
No, you're right.
Something bigger than X.
If F, yeah, why is that not working? So if F,
L is not a hypersurface in L.
yeah, that's true. But he's talking about condition 1. If S is clean intersection with L, okay, well, let me... So there's some kind of problem that I've made with this.
F is X.
Yeah, S is X, yeah. Let's see. Yeah, you're right. There's something strange, right? Okay, let me. I won't need that obviously. If I did, I would have figured it out. So let me just pause on that for a second. Okay, so. Okay, so these lifts. So okay. So let me. So let me give an example. So let me try to blow up the simplest groupoid. Okay? So let's look at the pair groupoid of an interval. So this is I cross I. This is the identity of I. Okay? And I choose a point in I. Okay? So here we just have the pair groupoid. I'll call this from now on pair of I. And I have this point. Now notice that the point in the interval is of codimension 1. However, this, which is the image of that point under the identity map, is of codimension 2. Okay? Therefore I can blow it up. I can blow up the pair groupoid of I along the identity applied to P. And of course, it's the same picture that I drew before. You get an RP1 inside there. Okay, now, if you take a look at the source and target fibers, so this is the source and target fiber of the pair groupoid, then the proper transforms of these will be these. So I'll call this S double bar and T double bar. Those are the proper transforms of the source and target fibers. So you'll notice that I want this to be a groupoid. That's the strategy. I want this to be a groupoid. So in order to get the source and target maps on this space, what I'll do is I'll just compose the blowdown with the source and target maps here. And that's the strategy that I'll use for all of the structure maps. If I want to define a multiplication, then I have to look at the multiplication here and make sure that it lifts to this blow-up using this universal property. That's the strategy, so that you always check that the groupoid operations lift. Now the first problem that you realize is that if you pick a point which is at the intersection of one of these source or target fibers with the exceptional divisor, right, then this point, there's basically two directions in the tangent space, okay, and this direction is tangent to the target fiber, and so it'll be killed by the derivative of the tangent of the target map down to the base. So this direction here is in the kernel of the target map, of the derivative of the target map, and this direction is the direction of the exceptional divisor, and the exceptional divisor is sent to a single point under this map, which means that this direction will also be killed by the derivative of the source or target map, right? So this means that this target map will not be a submersion. And we know that for a groupoid, for a Lie groupoid, we need source and target to be a submersion. So the solution is to remove that point. And that removes this, and I want to do the same thing for S as well. Okay. Now you'll notice that if I look at, so this is a groupoid, supposed to be a groupoid over the interval again. And now if I look at the source fiber of P, what I'm going to get is, let's say, this line, as well as the exceptional divisor, right? So as you can see, it's now disconnected. Okay? So I want a source connected groupoid. So just get rid of the connected component, which is annoying me. So what I'll do is I'll remove this and this, right? And I'll remove this and this. So those are just segments, right? So that, okay. And then now I've kind of, if you see, then I've totally disconnected this chunk, this vertical piece from this horizontal piece. So in fact, I can just remove all of this and all of this. And what I'm left with, sitting inside here, is this region here. So this is now a groupoid over the interval, like this. Okay, and if so this is an example of a blow-up groupoid, a groupoid obtained by blowing up, where the important point is that I blew up a subgroupoid.
I assume you have a product structure in mind. In particular, what is the isotropy group over the exceptional point?
So the isotropy group over this, so indeed, so if I redraw this in maybe a little bit more kind of suggestive way, here's the interval, right? The source and target fiber above this point is exactly this line segment. It's basically a copy of R star, okay? And so they coincide there. So we have source and target coincident there. And then the source and target, they kind of look like this. So and then like this. Okay, so the source and target fibers are generically transverse, but then at this special point where I did the blow up, they line up to be parallel. Okay, and so this explains why, for example, if you apply the Lie functor, right? And you take this bundle, the green bundle, right, and then project via the target map, right? This is an anchor map which drops rank exactly at this point, right? And so what you end up in this way, what you end up with, so this integrates the tangent algebroid twisted by P. So these are vector fields vanishing at P. Okay, so this is a construction which was fairly well known. For example, if you look at the work in Melrose or in Weinstein or those papers that I mentioned here. Okay, and this is a construction of a groupoid by blow-up. So we kind of wondered about how general this construction is, and so what I can say is that you get a kind of surprisingly general result. So here's a theorem. So this is in that paper I mentioned. Okay. So suppose that you have H inside G, a subgroupoid. So this is a closed Lie subgroupoid of G. And suppose that, so G is a groupoid over M, say, and this is a groupoid over a submanifold of M. Okay, and I want the codimension of L to be 1. The reason I want this condition is because when I do this blow up, I only want to blow up G, okay, in H. I don't want to change the base. If L had higher codimension, then I could blow up the base as well. Then we would be doing 2 blow-ups, okay? But in any case, so we have this closed subgroupoid. Okay, then we define. So then, I'll give it this name. So G colon H. Okay, this is defined to be the blow-up in H of G. Okay, and just as in the previous case, it's not enough to blow up. I need to remove any of the bad loci. Okay, and the bad loci are easy to describe. They're described by taking the inverse image of L under the source and taking the proper transform, and then do the same thing for T. Okay, so this is exactly what I did here. I blew up, and then I removed this fiber and this fiber, and then for good measure I also removed the disconnected component. So you could choose whether or not to do that. You could take the connected component of this or not. Okay, so the theorem is that this has a unique Lie groupoid structure such that P, the below-down map, is a morphism. Okay, and okay, so the theorem has a few more statements, but this is the important part. Okay, so you can blow up a subgroupoid over a hypersurface. But when you see something like this, there's a natural question that comes to mind, which is, if you can take a subgroupoid and blow it up and get a new Lie groupoid, then what is the Lie algebroid of that resulting groupoid? What is the Lie algebroid of G blown up in H? Okay, so to answer that, okay, for those that are familiar with it, you may be able to guess that the Lie algebroid associated to this blow-up is exactly the sections of G, of the Lie algebroid of G, such that when you restrict them to L, they're actually sitting inside the Lie subalgebroid Lie of H. Okay, so does that make sense? So H is a subgroupoid, right? So associated to H, there is a Lie algebroid supported on L, and that is a Lie subalgebroid of the Lie algebroid on M, right? And so if you look at the sections of the Lie algebroid of M, so that when you restrict to L, they sit inside the Lie algebroid here, that defines a kind of space of subsections, sections of this, it's a subspace of the sections of the Lie algebroid of G, and it turns out that this, if you wish, sheaf is locally free and forms a vector bundle, which is given by this Lie algebroid. So this motivates a definition, which is to say that if B over L over a closed hypersurface L is a Lie subalgebroid, then you can always produce, so this is codimension L is 1. Okay, this means that we can always produce a new Lie algebroid, so A colon B, which we call the elementary modification of A along B. Okay, is a new Lie algebroid. Okay, so Alan told me about some examples of this a long time ago, and I was looking for a kind of general construction of these, and so this is something that comes up naturally. So you can always kind of modify A by kind of twisting it along B in this particular way.
Your description of this, you stated in terms of sections.
That's right.
What is in terms of the algebroids?
That's a good question. I don't really have anything particularly intelligent to say about that. But the reason that we called it this elementary modification is because this operation on vector bundles is known in algebraic geometry. I mean, it's called elementary modification, or sometimes Hecke modification. It's a way of taking a bundle, taking a sub-bundle supported on a sub-scheme, and then twisting it in this particular way. So all I can say is that it's a well-known operation at the level of vector bundles, but I can't tell you that it's a fiber product of vector bundles over some other, you know what I mean? It's some other operation. I don't know. Okay, so with this type of result, you can really kind of proceed in a kind of interesting way. So you can say, so let's say we wanted to construct groupoids for these Lie algebroids. So suppose we start with the tangent bundle of M, right? And then what I said was that suppose M is a log symplectic manifold, right? Then I have T dm. So these are the vector fields which are tangent to D. And then inside here I also have this T star pi M. Okay, so we have this kind of sequence of Lie algebroids. This is the anchor map for this one, and the composition is the anchor map for the Poisson tensor. Okay. Now, we already know how to integrate this one. So this one integrates to, let's say, the pair groupoid of M. Right? Now, in order to understand how to integrate this one, all we need to do is to understand this Lie algebroid. Kind of note, so step 1. Okay, TDM is nothing but TM, so it's exactly the vector fields which are, when you restrict them to D, they're tangent to D. So that means that it's given by the elementary modification of TM along TD. Okay? So this tells me that if I simply, all I need to know in order to integrate this is to integrate this, and then take the blow up. Okay? So this means that if I blow up, or if I blow up the pair groupoid of M in the pair groupoid of D, then I get an integration of TDM. Okay? So it becomes a kind of calculus where you know how you're changing the Lie algebroid step by step, and then you just apply these steps to the groupoid by blowing up. Okay, and then in kind of step 2 is just to notice that that this Lie algebroid can be expressed as the elementary modification of this one, TDM, in a Lie algebroid which you get. So remember that D fibers over S1 via a map F, which, remember, it had these symplectic leaves. So I'll call the projection map to S1 F. Okay, and here I can take the fiber product over TD with the kernel of TF. So this is basically forcing the vector fields inside this Lie algebroid to be tangent to the symplectic fibers here, right? So that's all that this means. And so because of this, I can get I can blow up. So let me give this a name. Let me call this pair DM. Okay. So I can blow up pair DM in something that integrates this. It's not too difficult to see that what integrates this is this object, where the pair groupoid sub FD, what this means is that it's just instead of taking the product of D with D like I did before, I take the fiber product over S1. Okay, and that provides you an integration. So this integrates the Poisson structure. So it integrates the log symplectic structure. So okay, so the interesting thing about this blow-up procedure is this universal property. Okay, so whenever you produce a groupoid in this manner by blow-up, it's a very special one. Just like the pair groupoid, it tends to sit at the bottom of the tower of all integrations. Right? Normally, you have other integrations, like, for example, the source simply connected one. When you produce this blow-up, it typically sits. It's the terminal object in the category, so that any other groupoid which maps down to it. Any other groupoid will kind of map to this pair style groupoid. So the question. Let's say it like this. So the blow-up, which I'll just give a name. I'll call it pair pi of m. So this blow-up is a terminal object in the category of integrations. Okay. And so the question is, what are the other integrations? But there's an important thing to note about it. Is that it has a symplectic structure. Okay. So it is possible to check. If you're careful about how you do the blow up, you can easily check how the Poisson tensor, which here you started with the pair groupoid of m, and you blew it up. So if n was log symplectic, then this pair groupoid would also be log symplectic. And then when you do this blow up, it's possible to follow the Poisson tensor and see what happens to it. Okay, and at this stage, when you produce pair dm, this is also log symplectic. When you do the second blow up, this then becomes symplectic. It's very similar to blowing up in algebraic geometry. Typically, if you have a differential form and you blow up, that differential form will acquire degeneracies. But these are bivectors. When you blow up, you can remove degeneracies via blowing up. So it turns out that this thing has a symplectic structure, and this is an unusual situation. I mean, normally it's only the source simply connected groupoid that inherits a symplectic structure necessarily, and you have to check the intermediate groupoids whether they are symplectic. But in this case, even the lowest one is symplectic. Okay, so that is just the blow-up construction. So to get the remaining groupoids, you need to use a gluing construction. Okay, and so it turns out that the right notion in order to understand how you can glue groupoids together is a so-called orbit cover. So suppose that A over M is a Lie algebroid. Okay. And suppose that we have a cover of the manifold, an open cover, such that each orbit of A lies in some UI. So the orbit, the covering is arranged in such a way that every orbit of the Lie algebroid sits completely within at least one open set. In other ones, it could sit partly, yes. So the important thing is just that it is completely contained in at least one of them. Okay, and so what these typically look like, so if this is your degeneracy locus, right, then what you want to do is to take one open set to be, let's say, M minus the degeneracy locus, and the second open set to be a neighborhood of D. So you'll have a kind of neighborhood here, here, and here. Okay, this will completely contain those orbits, and then the rest of it will be one open set. Right? So for such an orbit, for such a covering, you have a following diagram. So this is a theorem. Okay. For such a covering, the category of groupoids, or the lattice of groupoids, can be described as a fiber product of the integrations separately on U and V, as long as you make sure that they agree on the overlaps U intersect V. Okay? And so this allows you to kind of reduce the problem of classifying all groupoids to classifying them locally with respect to one of these coverings, and then gluing them all together. And the final tool to put them all together is what we call the graph of fundamental groups. So what you need to do is you need to produce a graph of groups. Okay, so the vertices, okay, are you have one vertex for every component of M minus D. Okay, so if this was your D and M, then I would have 1, 2, 3 vertices. Okay, edges. You would have one edge for for each component of D. So here I would have one edge connecting this to this, and this component would be connected to this one with two edges, so I have two edges like this. And then I would also have half edges for the components of D with non-orientable normal bundle. So this is for orientable normal bundle. Okay. In this case, they all have orientable normal bundle, but for the CP2 case from before, for this case, I only have two vertices. I have one edge joining this to this, right? And then I have a half edge because this one is a Mobius strip, so I have only a half edge with no vertex. Okay. Okay. And then you just stick on this graph the fundamental groups. Okay. So for this vertex, I'm going to put the fundamental group of V, and here I'll put the fundamental group of V prime. And in the middle here, I have to put a fundamental group, which, depending on which Lie algebroid you're studying, would either be pi1 of the hypersurface, which separates V from V prime, or you could put pi1 of the symplectic leaf in that hypersurface if you happen to be studying the log symplectic manifold. So you'll put one or the other depending on which Lie algebroid you're studying. And then then for this half edge, you're going to put pi1 of V, let me draw it below. So here you'll have pi1 of V, pi1 of D. Okay, and then because of the fact that D has a non-orientable normal bundle, this means that the first Stiefel-Whitney class of the normal bundle of D is non-zero, which means that first Stiefel-Whitney class will have a kernel which sits inside there, and it's only this kernel that maps here. In this case, you get maps from this group to this group. Okay, so obviously I don't have time to go into all the details, but the point is that this graph is equipped with a bunch of groups and a bunch of group homomorphisms between them. And the theorem, the final theorem, is that, let me just write it here. So the theorem is that the category of integrations is given exactly by, there's an equivalence of categories to choices of normal subgroups which are compatible with the group homomorphisms. So the lattice of normal subgroups on vertices and edges compatible with mass. Okay? And so this kind of gives you a complete classification of the different integrations. And this compatibility condition basically states that when you choose your normal subgroup here and your normal subgroup here and one here, then when you pull back these two normal subgroups, the one you chose here has to be contained in both of them. That will give you an integration. But if those containments are equalities, then we get a Hausdorff condition. So the containment of the choices on the edges, inside the choices on the vertices, will specify for you explicitly when your groupoid is Hausdorff and when it is not Hausdorff. And so you can look in our paper for a bunch of examples where we work out, for example, what all of the Hausdorff integrations are for a given log symplectic manifold, and we continue from there. So I hope that these two methods can be useful to get a better geometric picture of what these symplectic groupoids are. Okay, thank you for your attention.